Assalamualaikum and very good morning. How are you guys? I don't know what time you are watching this video, but I'm doing it in the morning. Okay. So we have to continue. We have another two chapter left, which is chapter 11 and chapter 12. Okay. So to start with, okay, remember this experimental. You have watched my video and your lab. This one is lab number 7 and lab number 8. Okay. After the experimental, after you have watching the video, you are giving this kind of graph. This kind of graph is called a response. Okay. And from the experimental, it should come out from this recorder chart. However, I simplified it because we are not conducting the experiment physically. So I have simulate for you the response, which is from this block diagram in a simulating software. And then for your lab number 8, you have to simulate so that you get this sustained oscillation without understanding what's going on. Okay, what happened? Okay, when we have experimental, what actually happened here, and then suddenly we get this response. Same goes here. From this simulating into this response. Okay, what happened in this? Okay, what happened here? Okay, so what happened here is explained in this chapter. Basically, chapter 11. Okay, so chapter 11 is here to explain what happened when we have the process, whether physically or a simulation, and then we get a response. How to get that response and why the response is like that. Okay, so this chapter 11, will explain mathematically. Okay, it's very challenging to teach this chapter. It's also very challenging to learn this chapter because it's quite complicated. Okay, but don't worry. I try my best to explain to you. Okay. So, this is what chapter 11 all about. It's explain, it will show you how you should get this graph mathematically. Okay. So, taking into account this example, when we have a tank that we filling with a water, and then the control variable is the level. At the same time, there are fluid, the water is flowing out from that tank. Okay, this is liquid level control system. So, what I want to explain here is look like quite complicated. It's a lot of things. What happened here? What I want to tell here is when we have a process, okay, something like this. When we have a process, we do have this is a real process. Okay, and then from this real process, we draw this one. Okay, this is number one. Okay, when we have a real process, we can draw the PNID diagram. Okay, this is called PNID diagram or instrumentation diagram. Okay, it might not really the same, but I just want to show you that this is the real process. This is a instrumentation diagram. I will call it instrumentation diagram. And then we also have the third one, we have a block diagram. Okay, this is block diagram. Just like I said to you in the previous video, it is in a block shape. So this is a block diagram. Okay, and then this is a block diagram for the actual process. This one for the general. Okay, this one for general block diagram that apply for any feedback loop. This one is a block diagram for specific process. Here we have this level control system. Okay, you can see the difference. Okay, we have here GC, also here GC, but there are a percentage and a unit of each of the unit involved that process. Okay, this one is the general one. This one is the specific for level. And then here we have here equation 11.26 is called closed loop. Okay, it is called closed loop transfer function. Okay, both is a closed loop transfer function. One for the set point, one for the disturbance. Okay. So what happened here is when you have a process, okay, we have to draw a instrumentation diagram or PNID diagram. From that PNID diagram, you have to draw we can draw a block diagram. From this block diagram, we have to reduce this block diagram into a closed loop transfer function, and we have to solve this mathematical equation until we can get this graph. Okay. This is chapter 11 all about. I know it might sound complicated to you, but we try to go slow by slow. Slow by slow. We don't say that. We try to go slowly. Okay. So this is a general block diagram. This is a general closed loop transfer function that apply for any closed loop transfer function. And this one is for the specific case. Okay. Again, we have a process. This is an instrumentation diagram or PNID diagram. And from this PNID diagram, you should know how to draw this block diagram. From this block diagram, you have to do a block diagram reduction so that you get this closed loop transfer function for this process, and later on we have to solve it. Okay, we have to solve it because it is in the S domain. We have to convert it back into T domain, solve it, and we can draw this graph. So this is a step. Theoretically, this is what happened when you have a process. When you have a process, and from that process you get a response. So this chapter 11 is all about that. Okay, it's about how do you get this from a process, what is actually happen behind that. Okay. Okay, so don't worry, we go step by step. Okay, so this is the step. The first one is a standard block diagram for feedback control system. Okay, so this is the block diagram. Okay, I believe you already know what is GC. GC is a transfer function for a controller. GV is a transfer function for control valve. GP is a transfer function for process. GM is a transfer function of a measurement, which is a transmitter. And GD is a transfer function for disturbance. Okay, you have to familiarize with the term, which is we use a lot of word. I'm using a lot of word transfer function, and transfer function is G. Okay, so this another letter here represent what represent the identity, whether it is the controller, it is the transmitter, or even the process itself. Okay, so this is an alternative form of a standard block diagram. Okay, can you differentiate between these two? Okay, this one and this one. Can you differentiate? What are the difference between these two block diagram? Okay. So to start with, remember that you have a process. Everything start with a process. When you have a process, you develop a dynamic model. Okay, and from that dynamic model, you have to develop the transfer function. So this is the transfer function. How do we know it is a transfer function? Because it is always in this form. Okay, K over tau S plus 1. Okay. I will refer this to gain, and this one too, it's named time constant. Okay, so KC is a gain for controller, KV is a gain for valve, KM is a measurement gain. How about tau? Okay, tau is time constant. Okay, tau is a time constant. Okay, so time constant. Okay, a tau P should be tau P, which is a time constant for a process. Tau M is for the measurement, tau V for the control valve, tau C. We don't have tau C. We don't have that tau C. Tau C, it might be there, but it different meaning. Okay, that is we cover in chapter 12. Okay, so we have this transfer function, and we have all the definition. This is a transfer function for the process, which is your lovely stir tank blending process. Okay. And then from there, okay, so for the process, we have a transfer function for the process. Okay, how to get a transfer function from a dynamic model, that is another thing. That is a quite maybe a revision for you later on. Should be covered by me. Okay. And then, okay, so we have this block diagram. Okay, this is a block diagram representation. This is a instrumentation diagram. So this is the process. Stir tank blending process. Okay. And then this is a transfer function. This is a GP. This is a GP. This is a GD. Okay. How do I know? We have to go back to this one and go back to chapter 4, which is the transfer function. Okay, but now we are moving forward, not backward. Okay, let's moving forward first. Okay, so we have a transducer. Okay, so this transducer also have their own transfer function, but it is not first order, it just K. Okay, it is not K over tau I P S plus 1, it is just KIP. Okay, same goes with control valve. Okay, we have a first order transfer function. Okay, and then this one, first order transfer function. Okay, up to this point, you should know how to differentiate first order, second order transfer function. If not, you have to do some revision. Okay. Okay. Also same with transmitter. Okay. So this transmitter have their own transfer function. It should be first order transfer function. However, remember that we're talking about transmission delay. Okay, it shouldn't be a transmission delay. And then the value of tau m, which is a time constant, equal to or approximately 0. Okay, that's why left only km. Okay, so this time constant is also the time for the process, the time for the device to respond. Okay, and then we have the controller here. It is PI controller. How do you know? How do I know it is PI? Because we have here KC and only tau I. If we have tau D, then we have a derivative. Okay. So each of these element, each of these component in this block diagram, okay, in this block diagram, the controller have their own transfer function, which is KC 1 plus 1 over tau IS plus tau DS. If it is PID, it depends on which mode that we're going to use. Then we have a valve here. It could be a first order. So we have KV over tau vs plus 1. Then we have a transfer function for a process, k over tau s plus 1. Same goes with the transfer function for the disturbance, k over tau s plus 1. And then for the transmitter, we have k m. Okay, because the tau m is approximately 0. So each of these components have their own transfer function. Okay? So what you need to do is we're going to simplify all these transfer function into a closed loop transfer function. Okay, going back. Okay, so this is the block diagram for the blending process. Okay, so it's using PI mode here with a transducer, control valve, a process, and a disturbance together with a transmitter here. Okay, so this is a start off when we want to do a block diagram reduction. What is block diagram reduction? Block diagram reduction, which is from a block diagram, we want to change into a closed loop transfer function. Okay, from block diagram into closed loop transfer function, it is called block diagram reduction. Okay, so if you have sum, just sum c equal to a plus b, just like that, and we have a comparator plus and minus, c is equal to a minus b. When we have a block like this, it is a multiply operation. Okay, so y equal to g times x. Okay, and then if we have a block in series like this, okay, so the y is equivalent to this one. Okay, so this block diagram, these two block diagram can be simplified into this. Okay, still multiply operation. Okay, so this is a block diagram, a standard form, a general form, and this is for the specific process. Okay, can you see the difference? Okay, here we have a standard block diagram for feedback control system, and as you can see here, we have a letter and a transfer function for each of the component. Okay, so later on we're going to do a block diagram reduction. Okay, so here we have y as a control variable, u is a manipulated variable, d is a disturbance variable, also referred to a load variable. P is a controller output. Okay, better we see this. Okay, so P is a controller output, E is a error signal, we have a YSP which is a set point, we have YM which is a measured value of Y with a transfer function. Okay, okay, so this is standard notation. Again, the transfer function for everything, and yu and yd is a change in y due to u due to the set point change or manipulated variable. Yd is a change in y due to the d, which is a disturbance. You don't have to memorize this. Okay. Okay, the next step is we start our first step, which is a block diagram reduction. Okay. So as you can see here, x1 is here. Okay, x1 is equal to u times g1. Okay, x2 is equal to x1 times g2. Okay, and x3 is equal to x2 times g3. Okay, so just substitute this into this and this into this. Okay, so we can just directly substitute. Okay, let's see. Let's try. Okay, make sure you try yourself. Get a pen and a paper. Try yourself. Okay, x2. Okay, let's see. We start with x3 equal to x2 g3. So x2 is equal to x1 g2. Don't forget your g3 here. And then x1 is equal to u g1 g2 g3. Okay, so it doesn't matter whether you write it as a g1 g2 g3 or u, or the other way around, or you can even write it as you like, maybe like g1 g g3 g2 or u, it doesn't matter. Okay, so then we get this one. This is the first. Okay, you should try by yourself. Okay, and then we're going to start our block diagram reduction. Okay, let's start. So basically for this block diagram reduction, there are two conditions. Okay, the first condition is a set point change. Okay, when the set point change, we assume that there is no disturbance change, only set point change. In process control, there are always just two cases where the set point change, okay, or you have a disturbance change. So when you have, we assume it's occurs separately, but in reality it might occur simultaneously. But for this block diagram reduction, we assume it's occur separately. Okay, so for the first case is a set point change. When a set point change, the d is equal to 0. D is equal to 0. So start with this equation. Is this one. Okay, I will show it in my whiteboard. Here is my whiteboard. So let us start a block diagram reduction from this figure 11.8. Okay, where should we start? We should start with here, this one. Okay, as you can see, y is equal to yd plus yu. Just write it as yu plus y3. Okay, and then we continue. Yu is equal to, okay, you can see yu is equal to u times gp. u times gp plus yd is equal to d times gd. Okay, as you can remember, okay, when you have an arrow and a block diagram, okay, when you have it, this one d gd, this is yu. Okay, so this symbol means time. Okay, so that's why you have yu equal to d times gd. Okay, hope you get that. Okay, let us continue. Okay, what do we have for u here? Okay, u is equal to p times gv and gp. Okay, one thing that I forgot, when we have a set point change, okay, for set point change cases, okay, for set point change case, d is equal to 0. So straight away, this term is equal to 0. So we just have to continue. Okay. So y is equal to, what is p? P is equal to this one. E times dc. Don't forget your gv and ge. Okay. Continue again. Okay. What is e? Okay. What is e? Okay. So e is basically y as p minus y. Okay. To substitute, do you get it? Is equal to this. Okay. Because of this, put it another color. This one. So continue. So just substitute y as p internal minus ym. Okay. Copy back everything. GV and GP. Ini again. What is y as p internal? It is this one. Okay. Y as p am. Okay. How about ym? Okay. Ym is basically, this is also y here. Okay. This feedback line is also y. Okay. It is also y here. So we have y. Remember, this arrow means time g m. Okay. Copy back everything. So y. So we have to span. Okay. Time this one, everything time to this one. Okay. Do a expansion for this equation. So just expand everything. Y as p am gc dv p yes y gm gc dvn. Okay, make sure you have a pen and a paper. Make sure you write it. Okay, don't just listen. Okay, make sure your hand write it. Okay, so next step is we want to bring this term into this side. Why? Because we have y. Because why? Because we have y. Okay, don't get confused with that. So y is plus, because here is minus. Bring to this side, become plus y gm gc right side y as p am gc dv. Okay, so we factorize everything. Okay, factorize y. So this is the remainder. SP, just copy it back. Everything should correct the correct transform. What did I do? Can we can use? Hope you can still see it clearly. So we will get our final closed loop transfer function. Just arrange it in this form. I plus MC. Okay. So we get here is our name as closed loop transfer function for set point change. Okay, so we derive everything for the case of set point change. Okay, so we get this closed loop transfer function for set point change. Okay, so I hope you really try it by yourself. Okay, and then moving on to a disturbance change. For the disturbance change, you should substitute, okay, the YSP equal to 0. You can use the same method. You should start with the same, which is yd equal to yd plus yu, and this one, but this time d is not equal to 0. Okay, so you have to substitute again. You just have to derive again everything until you get until this point. Okay, until you get into this point whereby this is equal to 0, so you will eliminate this term. Okay, left only this one, this one. Okay, so you rearrange everything so that you can get this. Okay, try this by yourself and upload it in the Google form. Okay, I will create the space for you to upload. Okay, so here is the both. Okay, both for the set point case and for the disturbance case. Okay, and then it's here telling us that the denominator, which is this one, is the same. Okay, and then all these GC, GV, and GP, GM can be equal to GOL, which is an open loop transfer function. Later on, we will see why we need to simplify it further this. Okay, don't worry. Okay? So your first task is to get this equation and this equation. Make sure you try by yourself. Okay. Okay. So for the set point change and disturbance change, yes, it's occur simultaneously in reality. Okay, not equal to 0. But for the derivation above, previously we want to simplify the thing. That's why we assume this one for the set point change, d equal to 0. For the disturbance change, okay, YSP equal to 0. And a combination of this, okay, should be this one. Okay, that's it. The first step, okay. So this is a general expression for feedback control system, which me myself, I don't really like to memorize this. Just it's easier for me if you can derive from that block diagram. Just derive it until you get a closed loop transfer function. But you can still use this one. Just me, I'm not prefer. Okay. It will result the same, but you have to memorize instead of uh, derive it. It's better for you to derive it. Okay, don't memorize it. Okay,